So let's get started. So we're getting to the third part of my lectures. So about 1 hour on second-order metamaterials and how we encounter these multipole effects there, how we've been able to reach the electric-dipole response in the effective non-linearity, a number of ways how we can try to enhance the nonlinear response of these metamaterials or nanostructures, and then again some open questions and present challenges. And then after the break, we'll talk about individual nano-objects. So polarization-based nonlinear microscopy, cylindrical vector beams, so radial azimuthal polarizations. Then, if there's time, I think that we're going to talk about modes and resonances of nanoparticles, and again some open questions and let's say present and future challenges in this field. So let's get to the nanoscale metals. So plasmonics, that's sort of a hot research topic these days. And if you take a metal nanoparticle, its optical response in the visible and infrared spectral regions, it's dominated by the so-called plasmon resonance of the conduction electrons. So I can assume that the electron cloud, in response to the electric field, it moves collectively. And then you end up getting these so-called plasmon resonances. These resonances, they depend on the size and the shape of the particles. If you order them into an array, the mutual ordering and near field, far field coupling can play a role. And furthermore, if you change the dielectric environment of metals, you get a shift in the resonance. And that's the basis for plasmonic sensors. And so the fact that these resonances, they depend on the size and shape, and we're talking about particles from a few nanometers in size, maybe a few hundred nanometers. So basically, on a fundamental level, these plasmon resonances, they basically meet-type resonances of these individual particles. And now, if you bring in light into, let's say, rather arbitrary metal nanostructure, this is a two-dimensional structure on a substrate, you find out that the optical field becomes localized on the nanoscale to these so-called hotspots. So that means that, the nonlinear response, they scale with a high power of the field. And now, if this hotspot here, it's much stronger than the incident field, and we raise this to second, third, fourth power, something like that, we are certainly going to get an enhancement locally. And then, if you're smart or lucky, you might also get an enhancement when you average the response of the whole sample area or sample volume. The other interesting thing is that in these structures you're going to have really very strong gradients in the local fields, but also gradients in the material properties. And if you remember still from yesterday, these higher multiple effects are related to field gradients. So almost naturally, these nanostructures, they could be really interesting from the point of view of trying to enhance these higher multiple effects. I'm repeating a slide from yesterday about local field factors. So in traditional materials, remember, we can use oftentimes, especially if we have a dielectric host, we can use these almost spectrally flat Lorentz field factors that relate the incident field to the local field experienced by an atom or molecule. And then you might expect to have resonances in the atomic susceptibility or hyperpolarizability, as we say, for atoms or molecules. Now, in metal nanostructures, when you have these plasmonic resonances, it turns out that the local field factors, they're spatially dependent because the local field becomes concentrated into these hotspots. Furthermore, you might get a change in the field direction in the nanoscale. So basically, a given component of the incident field might contribute to another component in the local field. So these local field factors, they're actually tensorial, they're space dependent. And they're related to the plasmon resonances of the structure. On the other hand, the inherent nonlinearity of metals, it's pretty flat spectrally, again in the visible and near-infrared regimes. Therefore, if you try to figure out what the total or effective response of such a structure is, you find out that this inherent nonlinear response is almost flat, constant, but then you have to integrate over all space this factor that depends on these plasmonic local field factors at all the interacting frequencies, and remembering also that they're tensorial quantities. So very complicated interaction, but it's doable. So here, compared to traditional material, here we can expect to have resonances in the local field factors, but not in the inherent material response, a key difference. But this is something we can tailor by the size and shape of the particles. Okay, so we are interested in the second order response. And we've been trying to reach effective electric dipole response in such a way that we can control it by the size and shape of the particles. Therefore, we have designed this tough to see, but these are L's. Bob, these are nicer L's than yours. So far, at least, right? Okay, so we want to this.
Is in the eye of the beholder.
Okay, but you had made more complicated arrangements, right? Okay. So basically, here when we look at this at normal incidence, we break the symmetry in this direction, and we want to do the experiments at normal incidence, because if we came at some oblique angular incidence, there's a chance that we couple with the traditional surface nonlinearity, which we want to avoid. So we really want to understand how the shape influences the nonlinear response. So our basic shapes are this L shape, there's a T shape, we have used dimers and particles. Other people have played with, for example, with splitting resonators and so on. And there's, let's say, more advanced shapes are emerging now in the literature. And these are arranged in an array with a period of maybe a few hundred nanometers. And we are using gold as the metal. The thickness is about 20 nanometers. And then we put a protective layer of glass on top of everything. Whether it's a good idea to have this layer there or not, it's debatable. But we started doing it that way. And we know how to design the resonances using that sort of recipe. So we keep doing that. OK. Now, how to describe this theoretically? There's going to be much fewer equations today than yesterday, so take it easy. OK. So here we have the definition of the second order susceptibility. So we have the source polarization for second harmonic generation. Here we have the susceptibility, and then the driving fields at the fundamental frequency. And then on the nanoscale, all these quantities exhibit nanoscale variations. So it can be a very complicated interactions. So somebody might argue that, okay, these are the period is sub-wavelength typically, so these are effective media, metamaterials. And that would be a nice approach, but on the other hand, it turns out that even when you are in the regime where the period is less than wavelength, you might excite some types of surface modes and have some additional resonances and so on. So the excitation of the surface modes could depend on experimental details, so we have to be a little bit careful here. And of course, we know how to do this properly. We have to figure out how the incident field from free space couples into these local modes or local fields. Then we have to take into account the local nonlinear interaction, and then see how those local nonlinear sources radiate out into the far field. Conceptually very simple, but to do it in real life, it's a pain. It can be done analytically for spherical particles. It was done already actually in 1999, and there are other approaches more recently. And even now, for these more complicated structures, our group and other groups, they have been able to come up with numerical recipes, procedures how to do this. So it's doable, but it's a lot of work. Okay, so in order to describe our experiments, we cheat a little bit, and not only a little bit. So we define a new tensor, which we call nonlinear response tensor. So basically, conceptually, it's a nonlinear scattering matrix. And here, on the right-hand side, these are the radiation fields that we just control in the lab. And this, on the left-hand side, it's not the source polarization, but it's the outgoing second-harmonic signal. So basically, we forget what happens. We sort of hide everything that happens on the nanoscale into this tensor. And of course, this tensor is really more specific to the experiment than the sample itself. But we are able to hide all these nanoscopic difficulties. these are quantities we can control in the lab. This is something we can measure in the lab. This tensor includes all multipoles implicitly. On the other hand, we can apply electric dipole selection rules to the whole experiment here. And finally, if you are a believer in effective medium theory, this tensor is proportional to the effective susceptibility of the structure. So I think it's okay. So, and then how to do the tensor analysis? We come at normal incidence with weakly focused beams, so we are close to the plane wave limit. So what we can control are the x and y components of the incident field by wave plates and so on, polarizers. And then we can detect certain polarization, polarized components of the second-harmonic field. And now it means that we can fit any signal we measure into this model. So it's a second-order response, so we can have x component squared, y component squared, and then the cross term xy, all right? And if we are not able to fit the results into this model, something is going wrong. This is a completely general model. And then we can define these, the components of the response tensor in the xy coordinate system. And if we end up measuring, let's say, x plus y or x minus y signal, we just have to combine these tensor components in the proper way, and so on. And you just have to take my word that by doing enough of these polarization-dependent measurements, we are able to measure the relative complex values of these tensor components. It's just a tedious process, but it's doable. So we started working on this in, more than 10 years ago, in early 2000s, and we saw all kinds of funny things. Even the linear response was not what we expected, so the sort of the axes of the sample were not in the directions that we designed them to be. So there were some small axis shifts. In the second harmonic response, we measured signals that should be forbidden for an ideal structure. We measured different responses for left and right hand circular polarized light, which is related, actually, we come back to that later, to chiral symmetry breaking of the sample. And then there's a mystery statements. We measured different signal levels for signals that should actually be equivalent. So something was going wrong, and things that are going wrong were related to nanofabrication. So the quality of this sample, that was from more than 10 years ago when we got these samples, it's not, I mean, you have a lot of defects. And if these defects are biased, they break, for example, for this shape, the reflection symmetry with respect to the y-axis. And then when you break the symmetry, you get new tensor components and new types of effects and so on. Okay? So that's the basic idea. And then once we started figuring out what's going on, we thought that, okay, let's get back to these multiple effects. And we did an experiment where the idea is the following. And this is something maybe which complements something for yesterday also. And so we rely on different radiative properties of different types of multipole sources. So if you have an electric dipole here, and if you check out some electromagnetics book and see how that dipole source radiates into the far field, you find out that then in the far field, the electric component of the signal is in the same direction than your source. Okay? And then the B field would be at 90 degrees with respect to the E field, and here pointing in the opposite direction. Okay? Now, if you have a magnetic dipole source, then it is the B field that follows the source. So we would get something like this and this in the two opposite directions. And now you see already that if you measure the signal in, let's say, forward direction and backward direction, then here they might be in phase, but then they're going to be out of phase here. And finally, if you consider one type of a quadrupole source, so from two opposite dipoles, so there's no net dipole moment, but there's going to be a quadrupole moment. And if you think a little bit of this geometry, you find out that the quadrupole source behaves the same way as a magnetic dipole source. So it seems that if you measure directional signals in just like a forward direction and backward direction, we are not going to be able to tell the difference between a quadrupole source and a magnetic dipole source. But we should be able to tell whether those are in the game together and then interfering constructively or destructively with an electric dipole source. And this comes back to the idea also that I mentioned yesterday at the very end, that when you look at the various moments of the source, then if you have a dipole source present, then the magnetic and quadrupole sources are not even uniquely defined. On the other hand, if you go far away and measure the whole scattering pattern, then you are going to be able to tell whether you have an electric quadrupole pattern or magnetic dipole pattern separately playing a role. But just looking at the source moments, that's not really enough. And then if you just measure in two different directions, that does not tell anything of the whole scattering pattern. So we don't have enough information to tell a difference between quadrupoles and magnetic dipoles. Okay? So this is the experiment we do. We have to measure, so we are doing second harmonic generation using a femtosecond laser. There's polarization control for the incoming fundamental beam. And then we measure the second harmonic signals in the forward direction and backward direction. And of course, in order to collect this reflected direction in the backward, or reflected signal in the backward direction, we have to tilt the sample just ever so slightly off normal incidence. But we are at less than about 1 degree, so we believe that we are not really coupling to the traditional surface nonlinearity. It's not an important issue. And then we detect S-polarized signals in the two directions and compare the polarization-dependent line shapes in the two directions. And the point is that if we only had electric dipole sources, these two lines would have to overlap. They don't, so we have direct evidence of interference between different types of multipole sources here, in the sense of the effective response, sort of me-type response of the nanostructure. And the other thing is that by doing this polarization modulation of the fundamental beam, we don't have to compare absolute signal levels in the two directions. We can normalize both signal levels and just look difference in the normalized line shapes. And again, as I said yesterday, measuring absolute signal levels it's really difficult. So you want to do something which is more like a relative measurement. Okay. The other interesting thing is that the overall features are similar, so we can still sort of maybe conclude that we are still dominated by the electric dipole response, but we get significant contributions from the higher multipoles. Then we went on for a more complete tensor analysis of this case. We found out that in some case, for some signals, the forbidden part of the response, so the part which is not allowed for the ideal structure, dominates, and when it dominates, it has a very strong magnetic dipole or electric quadrupole character. And this is also, these forbidden signals are related to chiral symmetry breaking. And all these effects, they are due to surface defects. And we can build a hand-waving model for how these things come into the game. So this is an L, an ideal L with some surface bumps that break the symmetry. And now if we assume that we can treat these bumps as local dipole sources, which are retarded in the direction of measurement, and maybe have different strengths. So we go to, let's say, to two opposite symmetric positions on the particle. There's this bump here, and then there's another bump here, which break the symmetry with respect to this original symmetry axis. And we see how these elementary dipoles contribute to the radiation fields. Then we get something like this. We have a dipole 1, which is retarded by half of the difference in sort of in the some characteristic thickness or along the direction of propagation, and the other dipole 2, which is retarded with an opposite sign. And then when you talk about these higher multipole moments, you're really talking about series expansions. So we can expand this to lowest order, so we get the sum of the two dipole sources, and then another additional term here, which depends on the retardation. And this retardation is something that what you get when you do the quadrupolar analysis. And now, suppose that we are looking at the signal that should be, in the ideal case, forbidden. That means that P1 and P2 have opposite sign, so we would not have a dipole response. And without the retardation, even this term would vanish. So in the ideal case, the forbidden signal vanishes. But when you take into account this model for symmetry breaking, retardation, and so on, you get an effective dipole contribution and effective quadrupole contribution from local elementary dipole sources. Okay? We went further by breaking this nonlinear response tensor into electric dipole part, so EEE part, like what we discussed yesterday, and then EEM and MEE parts. We did not include the quadrupole parts because we include those in the effective magnetic response. Okay? And now the idea is that it's an XXX tensor, but if we are using the X component of the electric field, we are talking about the Y component of the B field. And also then for the signal field, the same thing. And then if we do the following 4 measurements, we measure the signal for metal side incidence in the transmitted and reflected directions. Then we flip the sample over by rotating about x-axis. Then we change the sign of the y-coordinate. And then if you look at how these components here transform, xxx is never influenced, but then when we measure in reflected direction, we know that the magnetic dipole emits differently in reflection, so there's minus sign here. Then we rotate the sample, we change the sign of this y, we get a minus here, and then again here there's a plus and minus. So basically, by doing all these 4 measurements in the same way, we are going to be able to decouple effects from these various tensors. And this is what we get. Here we have 4 signals which are almost overlapping, but not completely. And then when we go through this analysis using this model for the, let's say, just this X signal, X-polar signal, we find out that these multipolar tensor components are up to 50% of the dipolar tensor components. So in relative terms, these higher multipole effects are really strong here. Although you would think that this is a nice result, things are overlapping and so on. But in order to account even these small differences, we have to bring in these higher multipole effects. Okay, so this is sort of sad. We started working on this topic in like maybe 2001, 2002. The first multipole effects, if a paper was published in 2007. So you could argue that for 5 years we were just measuring defects, something that we didn't want to have. But those were the limitations of the nanofabrication at that time. And I have to tell that other groups who were working on this topic, they were also measuring the effects of defects, but they didn't want to highlight that in their papers. They said it's almost okay, and we get a really nice magnetic response or whatever and so on. Okay. Now, but nanofabrication, it's progressing. So the people who make our samples at the University of Eastern Finland, they got a new E-beam machine around 2010. And if you compare the original samples from 2004 and before to this one, I guess that everybody agrees this is a nicer L shape than this one, right? Okay? And then, just by going from this one to this one, we immediately saw that the second-harmonic signals are about a factor of 10 higher. And the reason is that we have less inhomogeneous broadening in the plasmon resonance lines here. The products are better defined. Here there are random variations which actually broadens the spectrum, and it's quite evident even in the spectra. And then the nice thing is that once we repeat this set of 4 measurements for this sample, here you see that all these 4 lines, they're completely overlapping. The implication is that we have been able to reach the dipole limit in the effective nonlinear response of these nanostructures. And the implication is that only now, at that point, where we're actually controlling or able to design the response. And this was really a key point, because from that on, we could argue that we can start designing the nonlinear response, tailoring them, and so on. Up to that point, it was whatever. But OK, that's the way life goes. Things get better. So now I'll just go through a couple of ideas that we used after this sort of the breakthrough point. One of the things that's been discussed in the community is that how do these different resonances come into the game? And another group who has done a lot of work on this topic is the group of Martin Wegener, a really important group in the whole field of metamaterials. He's at Karlsruhe. So they've been working on these splitting resonators, where the symmetry is also broken in this direction. And when they put different pieces of their work together, they argued that you really want to operate close to the resonance for the fundamental frequency, so your incident laser beam. But then if you try to tune the structure in such a way that you also have a resonance at the second-harmonic frequency, it's not useful, because that resonance just reabsorbs the generated second-harmonic light. That's a little bit strange, because you would think that if you have resonance, it acts also as an antenna, which helps in outcoupling of radiation from the structure. But a few years ago, their result was that it's not really useful. The other thing that they have been arguing is that in their structures, they always get the strongest response through the magnetic resonance of the splitting resonator. So when they excite the system with light which is polarized in the horizontal direction, and they tune the structure in such a way that they have a horizontally polarized resonance for the fundamental frequency. So then the other thing they try to do is that, OK, we want to enhance the overall response, so we have to pack these resonators close to each other so that the number density goes up. But the problem is that when they bring those particles closer and closer to each other, there's all kinds of coupling effects, which starts broadening the plasmon line. So you lose the quality of the resonance, which then takes the response down. And so there's a limit how far you can take that approach. So at that point, it seemed that, OK, we are a little bit in trouble, because it seems that there's no good way to really enhance the response. So we thought that let's try to bring in some ideas from a slightly different field, which is the field of nano antennas, which is also a hot topic. You know what this is? This here is basically so-called Yagi-Uda antenna. So if you're still receiving your TV or radio signal with an aerial, this is the way it looks like. And the way it works is that there's basically just for radio frequency, just metal wires of different lengths. And there's an element which is known as the feed. And feed is the element where you connect your electrical wire to drive the system or to receive the signal into your stereo system or something. And then you have these additional elements, reflector and directors, so-called passive elements, which further modify the electromagnetic environment of your system. And through the presence of these passive elements, you get very directional operation of the antenna. And of course, this idea has been taken to the nanoscale. There's a couple of interesting papers. Here, there was a polarization-based measurement. This is the feed antenna element, actually. A Japanese group, they were able to demonstrate the operation of a nanoscale optical Yagi-Uda antenna using a polarized measurement. I will not get into details. And then another really nice paper from the group of Nick van Hulst in ICFO in Barcelona. So they used a quantum dot as a source, which they brought close to the feed element. And indeed, by doing like a back focal plane imaging with a microscope, they were able to show that the emission out of the structure is highly directional, goes only in one direction. A really nice piece of work. So our idea was that let's still rely on this L structure, but let's bring into our array passive elements. Passive in the sense that they are centrosymmetric particles with no second-order response by themselves, okay? And we used two different designs for the L in order to have either Y or X polarized resonance at our fundamental frequency or wavelength. And then we picked rather randomly the design for this nano antenna or passive element, which is basically just a metal nanobar. So now our reference sample is this, only L's in a lattice with a period of 1 micron. Then to see how these passive elements behave, just an array of them. And then samples where we combine these nano antennas either in Y or X orientation. And if you look at the sample structure, we can focus our attention to tensor components YXX and YYY, which are allowed signals allowed by the symmetry of this structure. Okay. And to see how that it really works, here are just some linear spectra. So indeed, for the small L's, we get X-polarized resonance close to our laser wavelength. For the larger ones, we get the Y-polarized resonance at our laser wavelength. And then for the nanobars, we get a very strong resonance at 1500. And our laser is here. So note already that these nano antennas are actually non-resonant for our laser wavelength. Why? Because we didn't really design them too well. We just picked a dimension, something that we can easily make, see how things work out, and we'll see how it works out. Okay. So here are the results. So for the small one, we have an X-polarized resonance at the fundamental frequency, and indeed for the reference angle, the X-polarized signal is much, much stronger. It's more than 2 orders of magnitude stronger than the non-resonant signal. Then, if we bring in the passive elements in X orientation, so in the resonant orientation, we get a factor of 2 enhancement. It's not a killer, but a clear effect. On the other hand, if we change the orientation, so we are in Y orientation, which does not match the resonance of the L particles, almost nothing happens here. Then, for the large particles, the same thing. Now we are Y resonant. This is the strongest signal. The X input produces a much weaker signal. Then, the wrong orientation of the nanobars or nano antennas, we get a small suppression in the strong signal. Not much happens here. Then, the proper orientation of the nanobars, and again, about a factor of 2 enhancement. Okay, so the basic idea works. But why does it work? Here are the resonances for different structures. Just for the Y-polarized case. So here, just the reference sample. This is our Y-polarized resonance here. If we bring in the nanobars in X orientation, nothing happens really here. It's still the same as here. Maybe a little bit weaker resonance. But somehow the presence of L modifies the resonance of these nano antennas themselves here at the longer wavelength. And then this was the reference for the nano antennas. And then finally, if we have the proper orientation, proper orientation of the nano antennas, there's a strong coupling between the two resonances. So the strength of this resonance is boosted by a factor of 2. There's something between the two resonances and a distorted line shape here. And so what's going on here is that these particles, they interact through the lattice. And we can build a very simple model for this. So we can treat our metal nanoparticles, we can idealize them to be polarizable point particles with a polarizability alpha. And then the idea is that the local field affecting a given particle in the structure it has two contributions, or actually several contributions. There's a contribution for the incident field that comes from the free space, and then a contribution from the scattered wavelets from all the other particles. And those scattered wavelets, they depend on the dipole moment of each of the particles, and then there's like a Green's function that tells how this dipole moment at site J contributes to the local field at site I. And then when you work out the detail, you find out that the response depends on so-called lattice sum, which is just the sum of these of the elements of the Green's function or the Green's tensor. And by doing that, you find out that the effective polarizability of a given particle depends on the bare polarizability alpha here, and then on the lattice sum. And clearly, as you see here, we can have all kinds of resonances here in the denominator, depending on the sort of the relative magnitudes and phases of the bare polarizability of the particles and the lattice sum. And in our case, we had to modify this, let's say, hand-waving model in such a way that we take into account that we have two different types of particles with different polarizability. And furthermore, these particles are anisotropic, so we have to take into account that the polarizability is just not a number, it's actually a tensor. But it's doable, and by doing that, we get a fair agreement, reasonably, let's say even reasonably good agreement between experiment, the blue line, and the model, the green line. And the reason for the fact that the agreement is not better than this is because we are not taking into account all the details in the Green's function, or the so we're actually neglecting the effect of the substrate. When you have a system or you have some surface structure, a substrate, and then like maybe the ambient medium, the Green's function becomes extremely complicated. So we just simplified it a little bit, but it works. We clearly see the effect of coupling between the two different types of particles. But then finally, so why does it happen so that even this basically off-resonant nanoantenna modifies the nonlinear response of these active particles? The reason for that is basically the following. When we measure the extinction spectrum, we are basically measuring the imaginary part of the response, so the absorptive part of. If you treat the system as a Lorentzian oscillator, we are only measuring the imaginary part of the response, and of course you have the dispersive part or the real part of the response, and the wings of the dispersive part, they actually extend. They have wings that go really far from the line center and still interact with at our laser wavelength. And the nice thing now is that our effective polarizability is something like this, and this effective polarizability is going to determine the local fields in the structure. So it's clearly a complex quantity. The lattice sum is a complex quantity. The polarizability is a complex quantity. So by somehow optimizing the lattice sum and the polarizability of the individual particles, there's a chance that we should be able to enhance local fields and nonlinear responses without increasing losses in the system. It's a possibility which we have not fully explored yet, but at least if you look at the sort of the hand-waving arguments that go around these results, there should be such a possibility. And that's in the future plans for us. Okay, then the other thing I mentioned already is that the other people who are working on this field, and especially Martin Wegener's group and his co-workers who've been working on splittering resonators, they have really been emphasizing the role of the magnetic resonance of the structure in giving rise to really very high nonlinear responses. But if you look at the symmetry and the features of our structures, this L is not very different from the splitting resonator. We can also have these sort of circulating currents when we excite with X polarization, so the charge moves along this path. So clearly, this could also lead to magnetic moments in the same way as what you get in the split-ring resonators that have more like a, almost like there's like a third arm still coming into the game. But the general properties are the same. In our case, just using L's, we have never seen any difference between the dipole resonance, which is sort of in this direction for this polarization, and the magnetic resonance, which is for X incident field. I mean, it just depends on whether we are close to resonance or not, but we can get a high response for either polarization. So then the question is that is there something fundamentally different between the L and split-ring resonator? Nobody has done the experiment. Probably somebody should. It's going to be probably Martin Wegener or maybe then ourselves at some point in the near future. But we decided to do another experiment. So we designed also another shape. It's a T shape. And now this T shape does not have magnetic resonances, because there's not going to be a case where you get, because of the symmetry, there's not going to be a way to excite the system in such a way that you get oscillators only here or here. Because for this structure still, Y and X are eigenpolarizations, and we had to work in that basis. So we designed both L and T shapes in the following way. We designed the L to have a Y-polarized resonance, so the magnetic resonance, oh, I'm sorry, actually it's the dipole resonance for our laser wavelength. Then we designed this T shape, where this arm is really long, to have an X-polarized resonance, so this direction, close to our laser wavelength. And finally, by shortening this part of T, we came up with a structure that has both X and Y polarized resonance at our laser wavelength. And now, by doing polarization-dependent measurements, we should be able to see what types of roles do the different types of resonance play in these structures. And these are the results. There's a lot of stuff here. So this is the experimental result. This is modeling based on so-called boundary element modeling of the nonlinear response. And so let's just look at the results. So for the L, Y-polarized incident light, which is resonant, gives rise to a very strong response. Then X incident is non-resonant. We still get a fair response. And then we can also measure a signal which is X or YX, which is the same as X, XY. This is tensorial symmetry again. So in this case, only one part of the incident field is resonant, but the other one is not. And we get still a little bit weaker response. And now I'm measuring X-polarized signal. For the large T, what happens is that we have X resonance. Using X-polarized light, we get a fair signal. But that's funny, it's supposed to be resonant excitation. Why is the signal so weak? Y incidence, non-resonant, is almost equally good. And then suddenly, when we use mixed input polarizations, we get a strong signal. For the small t, where both polarizations are resonant, the same thing. For Y strong signal, YXX, much weaker. No reason why it should be weaker because it's still resonant. And again, mixed input, a strong signal. And really, we can model this, let's say, semi-quantitatively, really getting very close to the experimental result in terms of the relative signal magnitudes. Okay, and the reason is the following. This is really getting deep into the details of the local field distribution in the structure. The point is that for the T, when we come in with X-polarized light, we have an open path for charge oscillation only in X direction. So there's no cross-coupling between X and Y directions. And therefore, for this oscillation, this structure is similar to just like a centrosymmetric bar without this part at all. And therefore, there's almost no nonlinear response. We can also calculate numerically the local second-harmonic fields just after the particles. So we get, for x excitation, y components where blue is a positive sign, red is a negative sign. So we get local contributions. But then when you bring these contributions into the far field, these local sort of, let's say, hotspots are going to interfere destructively, and there's no measurable signal. Okay? Then for y excitation, we oscillate in this direction. We get a very strong local spot in the second-harmonic signal here. Nothing that would suppress that then after the particles. So there's a very strong signal that propagates into the far field. And finally, for xy excitation, we break the symmetry in such a way that when we measure the x-polarized signal, there's sufficient asymmetry in the local second-harmonic fields, near fields, that they are able to propagate with a net contribution into the far field. So the message here is that it's not only resonances, it's also the particle geometry, how that influences the local field distributions, how the hotspots of the fundamental field coupled to the hotspots of the second-harmonic field, how the elementary second-harmonic fields are able to radiate into the far field in a constructive way. So still a lot of things to work on, also opening doors for further optimization of the responses. Okay, then some open questions. So what is the origin of second-harmonic generation from these metal structures? I think that you can get really far by taking into account the local surface response. And that means that if you have a system, and that, if you remember from yesterday, in some sense, the local surface response is dominated by the local normal, 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 or ZZZ component in the local coordinate system. And therefore, if you have a structure that produces equal hotspots at two opposite sides, then these local responses give rise to second-harmonic wavelets, which are going to be out of phase, and they're going to kill each other in the far field. Okay? And then, of course, within this model, the total response would be obtained by integrating the local response of the shape of the whole particle. And that's the model we are using right now. We have tested whether it makes a big difference in the model if we include more surface tensor components, and the difference are surprisingly small. On the basis of yesterday, you could expect larger responses if you try to understand this in terms of the results we got for this flat metal film. Other people are trying to bring in also the bulk contribution with the higher multiple origins of this delta prime parameter. The problem is that when you read papers from different groups, it's really difficult to figure out what they mean by bulk contribution. Whether they bring this bulk parameter too close to the surface where it interacts with the surface gradients. And to my opinion, you should not do that, because computationally you can say that, okay, let's test the surface and bulk contributions. Then if you set delta prime to 0, you are going to kill the response from the true bulk, but you are going to kill the response also from the surface gradients. So you have to be careful in how you interpret these different results. Then still about resonances. So right now it seems that you want to operate close to the resonance for the fundamental field, that's for sure. On the other hand, a resonance at the harmonic frequency, it should act as an antenna, help, let's say, second harmonic light get out of the structure. But there are these papers where people say that it's just a loss mechanism. But it doesn't have to be that way. And to my understanding, there are some papers appearing very soon where people show that you can actually take advantage of the harmonic resonance also. Of course, ideally, you would try to design a structure that has resonance both at the fundamental frequency and, let's say, the second harmonic frequency or whatever output frequency. Then you have to make sure that the hotspots of the structure for the two frequencies, they overlap spatially. Because it does not help to have a source at the location where the second harmonic field is not able to sort of couple to the radiation field. And finally, this question about whether magnetic resonances are better than electric. Right now, our latest results suggest that no, but who knows? I mean, there's still a lot of open questions. And then finally, what are the ways to optimize the responses? We have played with quite a few things. One thing is that just by sample quality, because we get less inhomogeneous broadening, we got a factor of 10 in the response. Then there was a structure which I did not discuss today, where we played with the ordering of the particles in the lattice. So two samples which look almost the same. And there's a factor of 50 difference in the responses. That's due to lattice resonances or lattice interactions also. And finally, something which nobody has really tested experimentally yet. And this is totally, I feel totally stupid about this, because we published this paper about the numerical modeling using the boundary elements method already 4 years ago. And as one of the model cases, we used this L structure. And this is in the paper there. We just didn't look carefully. The point is that here Z is the direction of propagation of the field. And for a certain signal, I think for y tensor component for a given structure, this is the radiation pattern out of the structure. See, there's a strong peak which is off axis from Z direction. So we will be measuring close to not quite the minimum, but something which is not the maximum. So there's a good chance, but we should actually measure at a different direction than forward direction. On the other hand, right now our structure is such that we get transverse phase matching from different particles in the forward direction. So we should design the structure in such a way that we get a diffraction order at the second harmonic frequency into this direction. And that will be nice, because then we come at normal incidence and we create the second harmonic signal in an off-axis direction with a peak which is fully separated from the fundamental beam. Very nice possibility. Still to be done. And finally, the reason why we get this off-axis radiation pattern, what is the role of higher multipoles in producing that? Another open question. It almost has to be due to interference between different types of multipoles. Okay, I think I'm done for the first part of the lecture. So let's break for 10 minutes and then we'll go on, right? So we're ready to move on to the final part of my lectures, and we're going to talk about individual nano-objects. But before we get into that, I'm going to go back in my life for about 20 years, which tells you the motivation why we end up getting into microscopy and nano-objects. And this is related to chirality. So you saw this slide already. Chirality, handed objects, and especially when you talk about molecules, you can have a certain chemical formula in two different forms, right and left-handed forms. And these are known as the enantiomers. And the reason chiral molecules are important is because we are all built out of chiral molecules. I mean, DNA, amino acids, sugars, a lot of natural molecules are chiral. And there are all these speculations about the original life being related to handiness. And the amazing thing is that biological molecules, they are enantiomerically very pure. There are estimates that in nature, the contrast between, let's say, the natural form and the opposite form is 10 to 15. So what is the reason for the chiral purity of life? That's one of the big questions, actually. The reason this is also important is that a lot of the drug molecules are chiral. But when you synthesize a given molecule, you get 50-50 mixture of the two enantiomers. But their physiological effects, or the treatment effects, are very different. And there's a famous example from the 60s. I don't know, have you heard about thalidomide? A drug whose one form is a very good medicine for, I think it's a sedative, but also for morning sickness for pregnant women. But then the other form of the thalidomide gave rise to birth defects. And there are other examples. So the other form could be a really good medicine. The other could be a poison. And right now, there are drug companies who wait for the expiration of patented molecules, which have been patented as a 50-50 mixture. And once the patent expires, they try to purify and re-patent only one-handedness and make a business out of that. So it's a nice business because the basic things there already. You just have to purify it. Okay. So chirality, it's a very interesting topic, important topic from a different point of view. And let's get back to surface and thin films. So if you take chiral molecules and put them on a substrate, let's say by spin coating, you expect to get a sample which has full rotational symmetry about the surface normal, but there could be an axis pointing along the surface normal. And when you work out the symmetry groups for these chiral surfaces, you find out that you can classify the tensor components into two groups, so-called achiral tensor components, which are allowed for any isotropic surface, the ones we discussed yesterday. But then you're going to get additional tensor components which are related to the handiness, and those tensor components, they change sign between the two enantiomers of the sample. And it turns out that if you do just traditional surface second-harmonic generation from a chiral thin film, you find out that the response is different for the circular polarizations of the fundamental beam, and this difference arises from interference between the achiral and chiral tensor components. And therefore, the effect changes sign for the two handinesses of the molecule. And the most interesting thing is that this effect is actually electric dipole allowed. There could be magnetic contributions, but it is electric dipole allowed. And linear optical activity, the index of refraction for the two circular polarizations is typically different. The difference is about 10 to minus 4 or 10 to minus 3. So it's a weak effect. Here, when you do second-harmonic generation, the difference in the signal for the two circular components of the fundamental beam can be of the order of 1. So this could be a really sensitive way to measure handiness of chiral molecules. So I was working on this in the early 90s, and at that time we just were working with chemists who produced or were able to provide us with just the right molecule to do these experiments. So this here, I don't have the chemical formula, but basically we used molecules which are known as polyisocyanides, and they were a chiral. And here's the experiment. So we measured S and P polarized signal, for example, in transmission, and we modulated the state of polarization of the fundamental beam with a rotating quarter-wave plate. So here, for example, we want to have right-hand circular polarization, here left-hand, and so on. And sure enough, there's a difference of maybe 20 or 30% compared to the average signal. So we define the normalized circular difference response like this. So the difference divided by the average signal level. Then, for the other signal, the difference here is here in the valleys, But here the relative difference is even larger. It's probably of the order of 50%. So very strong effects indeed. Okay, so the basic idea seems to work. But it's not so easy, because if you are characterizing a new unknown molecule or sample, you don't know what type of sample you have. Our technique is based on the assumption that there's isotropy about the surface normal. But if you don't know it's isotropic, it could be something else. So the problem is that you get funny effects if your sample is achiral but anisotropic, and then you build an experiment where the experimental setup has handedness. And these effects are well known, for example, in photoelectron emission from anisotropic molecules. So the point here is that we have a molecule with a well-defined axis. We come in with light from here, and then we measure photoelectron emission in a funny sideways direction. And now this experiment is defined by the incoming wave vector, the molecular axis, and the direction of observation. And if you look at this big picture a little bit, it's clear that you can make this experiment to have either right-handed geometry or left-handed geometry. And if there's handedness, you're going to get a different response for the circular polarized incident light in photoelectron emission. In our case, if our sample happens to have an anisotropy axis in the plane of the sample, we can end up with a handed geometry. So here we have the surface normal, which is one vector. Here the incoming wave vector, and then the in-plane axis of the sample. And now, if you look at these vectors, if you then take the sample and rotate it from this orientation to this orientation, you change the handedness of the setup. Okay? And it turns out that this can also lead to circular difference effects. And again, in the 90s, we were still lucky. So we had this molecule that produces so-called Langley Broadset films with in-plane anisotropy axis. So this molecule, we call it DCANP. It's a long chemical name. It's achiral, but the sample we are able to make is going to have an axis. And sure enough, if we make this experiment for the two handednesses of the experimental geometry, we get a, let's say, 15 to 20% CD circular difference response here. And then when we change the handedness of the geometry, the sign of the effect is reversed. So interesting physics, interesting effect, but a big problem if our interest is to characterize, to determine handedness of chiral molecules. Because if we get a new sample, how do we know that there's no anisotropy? Therefore, we have to come up with new types of geometries. So clearly, we have to be able to avoid any possibility of handed geometry of the experiment. That means that we have to come at normal incidence, and our experiment otherwise must have full azimuthal symmetry about the surface normal. Okay? So in principle, we could come in with circular polarizations at normal incidence. And then clearly, for the circular polarization, it does not matter what the orientation of the sample is. It does not matter. The problem is that this chiral surfaces have such a the structure of the nonlinear tensor is such that you need field components along the surface normal. And if you come with a plane wave at normal incidence, you will not have those components. So there's no second order response. But if you focus your field, even if you focus linear polarized light, just from ray optics, you can predict that at the geometrical focus, your polarization is going to be the same linear as you come in before focusing, but then slightly off from the geometrical focus, you are going to have longitudinal components in the local field. and they point in opposite directions on the, let's say, the bottom and top side in this figure. But when you square +1 and -1, you get the same. So these components are able to drive the surface nonlinearity so that you get a net effect. So that's a nice new possibility that we can try to utilize. Now, if we start playing with focused beams and polarization, you open a completely new box of all kinds of possibilities. So first, traditional laser beams, their states of polarization are homogeneous, meaning that the state of polarization at any point in the beam cross-section is the same. So for example, linear polarization, circular polarization. But you can also produce these high-order polarization modes. The most well-known examples are radial polarization and azimuthal polarization. And in radial polarization, the local polarization is linear, but the direction is in the radial direction along the beam azimuth. And then you can have a local linear polarization which is along the tangential direction, and this is known as the azimuthal polarization. I have no idea what the orbital angular momentum of these beams would be. Does somebody know? Okay?
We can work it out.
Well, okay. The radial polarization is really interesting because if you focus that, again from geometrical optics, you bring in rays in, and they add up in such a way that at the geometrical focus you get a really strong longitudinal component. A really interesting possibility to drive the surface nonlinearity. But we are not done with the possibilities. Remember that in order to address chirality in an unambiguous way, we want to have full azimuthal symmetry about the surface normal. And then we can use circular polarizations, but we could also build these high-order hybrid modes. So we could have a mode which is between radial and azimuthal polarization. And clearly, I guess I could call this twisted polarization. This twisted polarization can occur in a right-handed form and left-handed form. We could also have local circular polarization going at different phases along the azimuth. And again, you have a right-handed and left-handed possibilities here and so on. And we looked at this from theoretical point of view, and we showed that any of these possibilities where we maintain the azimuthal symmetry about the surface normal is an unambiguous probe of chirality. So we tested it by using model samples which are chiral and anisotropic and achiral and anisotropic. And there was no sensitivity to anisotropy, but there was sensitivity to handiness. And we did an experiment. So far we have done the experiment for using circular polarized light. So amazingly, again, at that time, this was just a few years ago, we happened to have available just the right samples. So we had, the key samples are achiral and anisotropic, and chiral and anisotropic. And now, if you use this again, the achiral anisotropic sample, and we use the quarter-wave plate to modulate the state of polarization. So we start from linear, we reach circular here, the other circular here, and so on. If our sample is achiral but anisotropic, the signals we record as a function of polarization, they depend on the relative orientation of the incident polarization and the sample anisotropy axis. But in every case, for the circular polarizations, we always get the same response. So there's no circular difference response. For the sample, which is chiral and anisotropic, sure enough, there's a very strong circular difference response. So this basic idea works, at least for circular polarizations. And then we have taken these ideas further to different types of samples. Carbon nanotubes. So we had some colleagues at another university of Finland They were heavily working on carbon nanotubes, and they sent us this sample where we had a single-wall carbon nanotube with well-characterized structural properties and chiral indices of 42.1. Chiral, I mean, I don't know how much you know about carbon nanotubes, probably more than I do, but I mean, they can, I mean, these chiral indices really tell whether, a lot about the other physical properties, like whether they're metal semiconductors and so on. Chiral indices 42.1 means that symmetry is broken, but only very weakly. And we have had this sample where the nanotubes were suspended over this like an opening in the membrane, so that there was no perturbation from the environment or the substrate that might break the symmetry. And here we were able to get signals out of the nanotubes. It's difficult to see here. The signal to noise ratio is awful. It's like 2, but I mean, you can still see that there's something. The question is that why do we get the second harmonic signal? Is it because of chirality? Chirality breaks the centrosymmetry, so that could be the origin. We could have some defects or deformations in the tube, or, if you remember from yesterday, we could get a response even from a centrosymmetric structure due to these higher multipole responses. So on the basis of these first measurements, there's no clear evidence about what's going on. We got new samples, a set of samples, and there's a lot of stuff here. The point is that so-called armchair structure is achiral, and this set of samples had an armchair tube somewhere in this regime, and there's no signal for any linear polarization or circular polarization. The zigzag tube is also achiral, and this is, well, this is, let's say this goes to the border of belief, but there's something. So this tube here is, there's a chiral part here, and the section which is only zigzag, individual tube. And the zigzag part has almost nothing. The contrast in this room is really bad. And by playing with any polarization, there's almost nothing here. So right now it seems that when our sample is achiral, there's no signal. Then this set of samples, I mean, these are random, I mean, there's no controlled way of making these samples. So you try all kinds of things and you get whatever you get. But here we have samples which are double wall tubes with pretty well-defined chiral indices. And here, for example, we get a very strong response for linear polarization along the tube axis. And here, the orientation is tilted, so we get a response for, let's say, vertical and horizontal polarization. Here, we get a somewhat stronger response for this circular polarization than for this one. And here, amazing, this tube here really likes, let's say, right-hand circular polarization, and really very much dislikes the opposite circular polarization. There's nothing. And these are chiral tubes, so this is interesting. We get a strong circular difference response from these chiral nanotubes. This is what you expect to have. And I could stop here, you would be happy, a really nice technique. The problem is that the circular difference response arises from interference between the chiral tensor component and the achiral tensor component. So what is the origin of the achiral tensor component for this sample here? It could be the fact that we have these two double wall nanotubes. They are not centered with respect to each other. So there's broken symmetry in some direction. We don't know, but that's a possibility. So a very nice result experimentally, makes a lot of sense, but when you think a little bit deeper, you are, right now we are still a little bit in trouble with this one, but we are working on that, okay? And we hope to get some other characterization results on these samples. And I think it's not shown here, I think we also have a sample which was single-walled chiral that somehow matches with all the other results. The others, I'm now moving towards individual metal nanostructures, where we are trying to address individual particles. And here, this is still about chirality. So we got chiral nanodimers from Martin Wegener. So the idea that this is a double layer structure, and again, it's very difficult to see here. There's too much light. But we have these crosses, and these crosses have mirror symmetry as such. But if you make a double layer structure where one cross in one layer has sort of this orientation, and the other one is slightly twisted, actually it's 22.5 degrees, which is sort of the optimum. You can do it this way or the other way. So you can produce a left-handed nanodimer or right-handed. And Martin Wegener, they were really proud about this structure. It was a beautiful, chiral, optically active nanostructure from the point of view of the linear response. And they sent it to us for microscopic measurements, where we basically used linear polarizations to see what we get. And this is what we get. This is, we scan the sample under focused laser beam, where the beam before focusing is circular polarized. And clearly, this left-handed structure, on the average, it likes more left-handed circular polarization than right-handed circular polarization. And the right-handed dimers, on the average, they prefer right-handed circular polarization. But these images, they look awful. I mean, there's a lot of inhomogeneity, a lot of variations in the signal levels between different particles. And when we first sent these results to our friends in Karlsruhe, they were a little bit unhappy because they thought they have really beautiful, nice structures. But then, the amazing thing is that when you calculate this normalized circular difference response, so you calculate for each pixel the difference between these signals and divide by the average, you get an image which is much more homogeneous. So in spite of these fluctuations in the individual signal levels for individual particles, we are still able to recognize the handedness in a pretty reliable way. And the fact that this works out so nicely, it actually tells something about the character of defects that we have. So most likely the defects are, it's related to surface roughness, which we think mainly sort of modifies the Z component of the local fields and respective tensor components. And this Z component is always in the game, and therefore when you ever calculate this normalized response, that part of the response sort of averages out. Okay? Then, getting further, we have also made nanostructure of higher symmetry and tested the use of radial and azimuthal polarizations in addressing these structures. And we started with a nanobump, which is ideally, it's a hemisphere with a 160 nanometer diameter and height of 80 nanometers. And they look reasonable. And then, if we image such sample, I think the period was 2 microns, so that we can easily address individual particles. If we image this sample using linear polarizations, sometimes we get more signals, sometimes a little bit less, but that's it. If we image the sample using azimuthal polarization, in general we get this donut-shaped image. And also, if we image them with radial polarization, we get the donut shape. But note that sometimes the symmetry of the donut is broken. And for example, for this particle here, what you get using azimuthal polarization and radial polarization, these distorted hotspots are somehow they're sort of orthogonal to each other, the patterns that we get. And so the point is that if we combine these results with numerical modeling, using our codes and so on, we can test an ideal structure, a little bit distorted, sort of an elliptical structure, a hemisphere with a defect, well, let's say a hemisphere with a huge defects, so basically almost like a merged dimer or something, 2 defects, and so on. And now if you use linear polarizations, you just measure something. The pattern doesn't tell anything about what's going on. You just measure something, and the signal level might vary a little bit and so on. And experimentally, it's even difficult to say whether there's any ellipticity in the image, as you can ideally see here. But then, by using azimuthal and radial polarizations, no matter how you break the symmetry, you get really unique features in the image that you record. And for example, if we try to understand what's happening for this particle here, for radial, it's something like this, so we are somewhere between these choices. For azimuthal, this is stronger than this one, so it's not quite as extreme as this one, but it's not this one either. So we are somewhere in between here, so this tells that maybe somewhere in this direction we have a pretty big defect, and so on. And of course, these possibilities are a little bit too rich. I mean, we cannot build a complete library about all the possibilities, but there's an amazing sensitivity to the morphology of the structures. And the other reasons, why do we ideally get a donut? The reason is that we have to bring this local linear polarization, for example, to the center of the nanoparticle. And when the particle is centered at the center of the focus, we get almost nothing. And so basically, when we scan this donut, even the focused donut, over the particle, we end up with a net image which looks like the donut. So you have to think a little bit how to interpret these results. We also did the same experiment for nanocones. Cones are different from the bump, that this sharp tip of a cone, it attracts local fields which are polarized along the tip axis through so-called lightning rod effect. So a lightning rod attracts the field lines to the tip and so on. And here, again, experimentally, with azimuthal polarization, we get something like donut. It's not ideal. Theoretically, we predict a donut. But with radial polarization, which, if you remember, produces this strong longitudinal component right at the focus, that couples strongly with the tip axis or nanocone axis, and we get a hotspot right in the middle in the experiment and also in theory. But our samples, they are not ideal. So here we have an SCM of a defective nanocone, which we try to model using such a structure. And here the hotspot is slightly offset from the ideal location. And then with azimuthal, you get this double lobe pattern, which you can, for example, find somewhere here to some extent. So again, this is another proof that this, when you use these high order polarizations, you get this highly enhanced sensitivity to the structural features of these nanoparticles. Okay, then let's move on to different ways of coupling light to nanotips. A lot of people are working on nanotips from different points of view. People like to, like Christoph Lienau, he's in Oldenburg in Germany, he likes to see how the electrons come out of the nanotip and so on. Really very fancy studies and so on. The question is how to get light into the nanotip. So basically, what you want to have, you need a field component along the tip axis. So therefore, you need to bring in, let's say, a plane wave from some sideways direction. Or you could use radial polarization. I like using radial polarization and focusing that, but you could argue that still these are experimentally awkward techniques. Especially if you want to do microscopy, you don't want to come from here. You have to come at normal incidence. But then we have to remember that the optical response of any structure depends on its symmetry. So we came up with this idea that if we break the symmetry of this nanocone by adding a base here, we break the symmetry, and then we could come in, even with linear polarized light, with forces the charge into here. If you have a quick look on this structure, it looks like an L. And we understand L's from the other context, from the previous lecture. Basically, L is roughly going to have two eigenpolarizations in the plane of this picture. One in this direction that should give a resonance at a long wavelength, and the other one somewhere here, which gives rise to resonance at a shorter wavelength. Because this blue one is this sort of like a magnetic resonance, and the red one would be in-phase oscillations along the cone and the base. Okay? This picture here, I'm cheating a little bit here, because this structure is not an ideal L. Symmetry is broken. It's actually also, in some sense, handed in this plane at least. So these eigenpolarizations are actually going to be elliptical, not linear. But just to illustrate what's going on, this is roughly something what we can expect from here. And such samples can be made. These samples were made by at the Max Planck, whatever institute they have in Stuttgart for, I think, for solid state physics. By Markus Lippitz, actually, he was the collaborator there. And we did both linear studies and second-harmonic microscopy on these structures. And now, when you just measure the spectrum, you can identify this blue resonance in this direction, very strong at 1200, almost 1300 nanometers, and then a transverse plasmon at about 630. But remember, then, if you look from this direction, we should also have two resonances. And numerically, from numerical modeling, this resonance should be at 710 nanometers. But if we measure the spectrum, this is theory modeling, at normal incidence, there's nothing. So we have to come from some off-axis direction in order to be able to couple with this resonance. And we come at plus 15 or minus 15 degree angle of incidence, we see an additional feature. And in experiments, at 0 angle of incidence, maybe something, and then at some angle of incidence, just a little bit more something, not much, but we somehow measured that. Okay. And then we did microscopy using radial and azimuthal polarizations. And now, one thing that I did not mention yet is that when you focus azimuthally polarized light, even in the focal volume, you maintain this donut shape, and you only have transverse field components, so XY components, no Z components. Therefore, when we use, let's look at the modeling first. When we do imaging with azimuthal polarization, we expect two lobes on opposite sides where the local polarization couples with this blue resonance, which is closest to our laser wavelength. That's the modeling. This is the experiment. And there's some, it's not perfect. There's some symmetry breaking, but it's roughly the same, the pattern we expect. Then, using radial polarization, when we move ourselves around in the focal volume, right at the center, we only have the Z component. When we go away from the center, we also have X and Y components. And in the end, the local polarization off-axis is going to be elliptical. But it's such an elliptical polarization that it's going to enhance the coupling to this resonance on one side and suppress the coupling on the other side. And we can model that numerically. We expect a contrast of 1.3 here. Experimentally, we measure a contrast of 16. So for once, experiment works better than theory, but whether it's a good thing or not, I mean, that's not completely clear. But it's working, and the reason that we have these discrepancies is, of course, that the real samples are not ideal. There's all kinds of defects and additional bumps. But the point here is that by lowering the symmetry of our particles, we can modify the nonlinear tensors we can access, and then by that way we can control the coupling of incident light. We can enhance the coupling or suppress the coupling. And actually here, nonlinear microscopy is just a very sensitive way to see how well we couple light into the structure. Okay, then something very different. This is in some sense almost the final part of the talk, about the concepts of modes and resonances for nanoparticles. If you take a Fabry-Perot, cavities waveguides, then you know, if you study any optics, you find out that you're going to find resonant modes at certain discrete frequencies which are supported by the structure. The reason for you get this result is because, mathematically speaking, this is a compact system, meaning that it's a bounded and closed system, so we have well-defined boundary conditions that tell us how the electromagnetic fields have to behave. If you're looking at the scattering system, you bring in light, you know it has to go somewhere. You always produce a scattered field. And then, again, mathematically speaking, your geometry is bounded. Your light goes somewhere far away, always. And in the end, you have an outgoing spherical wave. And then, independent of whether you have, let's say, a plasmonic resonance for a metal particle, you are going to get some type of a response at any frequency. Here you only get a response at discrete frequencies. It turns out that, again, mathematically, you can try to formulate an eigenproblem for this system in quite a few different ways. And there are actually still open mathematical questions as how to do this, especially for plasmonic systems. For perfectly conducting bodies, it's better defined. But for, let's say, dielectric scatterers and even plasmonic systems, there are open questions. Then, if you read literature from the plasmonics community, metamaterials community, people talk about all kinds of plasmonic modes. And then they're somehow thinking about how the charges oscillate within the particle. So they are somehow thinking about the quantum wave function of the electrons within the particle. But this approach is really not compatible with, let's say, classical electromagnetic theory. And for example, this mode here, this is so-called dark mode. What does a dark mode mean? Dark mode means that if you bring in linearly polarized light at normal incidence, you don't couple light into the structure because these two dipoles are out of phase and there's no coupling to linear polarization. If you come at some oblique angle of incidence so that you're going to have some retardation or phase difference between the extension of this one and this one, you can excite this quadrupole mode or dark mode. Okay. Then, when people talk about resonances, they say, okay, you have a strong plasmonic resonance at a certain wavelength or frequency. And that's fair enough. That's what a resonance means, that in some sense, the response becomes strong at a certain frequency. That's a resonance, right? But oftentimes, this analysis is actually based on a plane wave incident field, whether a plane wave excites the system in a proper way. For example, this structure here would be excited very differently with focused beams a beam at some, as I said, at some angle of incidence and so on, things like that. So what we wanted to understand is that is it possible to define electromagnetic eigenmodes for scattering systems as inherent properties of the particles without assuming any form of the incident field? It turns out that it's possible. The possible is that it's possible in a number of different ways. And the way we do, the basic approach is the following. We cannot do we cannot get a bounded system in all space, because we always have this scatter field going into infinity. But you can formulate the scattering problem using so-called surface integral methods. So you basically first solve the electromagnetic problem at the surface of the particle, and out of the surface field you know how to produce the fields inside the particle and also the scattered outgoing fields. Now the nice thing is that the surface, mathematically, it's a compact system. So it's bounded and closed system. The problem is that you can still attack this problem using a number of different formulations. And in our first approach, we took so-called Müller formulation for this problem, and this tells everything to you. So it's an eigenvalue problem, and all the complications are hidden into this operator A. And I can tell you that if you thought that the tensors are ugly yesterday, this is going to be much, much uglier. I mean, it's awful, really awful. Okay? The nice thing about the Müller formulation is that it's compatible with me theory for spherical particles. So we can check out this. This is certainly a nice feature. But there's a problem. We can produce, we can find eigensolutions. We can show that the solution with small eigenvalues have the potential of becoming strong. But of course, for this strong response, you have to be able to couple light into that particular eigenmode. Another important thing is that at any fixed frequency, you are going to have an infinite set of eigensolutions, which is very different from a cavity problem, where you just have one eigensolution, or maybe two if you take into account the polarization, for a certain frequency. Here, for any fixed frequency, there's an infinite set of eigensolutions. Okay. And there's a remaining problem. We have not been able to show that the eigenfunctions we get out of this approach form a complete set. That's the remaining question. But in any case, so we have used this approach as an example for gold nanodiscs at a fixed frequency. So the nanodisk has a diameter of 120 nanometers. I think that the thickness was about 30 nanometers or something, 20 to 30 nanometers, and a fixed frequency of 3.14 petahertz. I don't remember why the student picked this number, but okay, in any case. Now, these eigenmodes, eigensolutions, they are ordered by the eigenvalue of the solution. And so the system was designed in such a way that the smallest eigenvalue, so the possibility for the strongest response, it's this dipole response. So this is the charge distribution of the eigenfunction. So clearly this is a dipole mode where the charge oscillates back and forth like this. And of course, because of the symmetry, it's a degenerate mode, so you can also have oscillation in the orthogonal direction. Okay? Then the next one is actually a magnetic mode. So this here is so-called equivalent magnetic charge density, which means that we have local like eddy currents that circulate like this, which can be described qualitatively, or which can also be described in terms of like magnetic charge density, if that exists, but they arise from surface currents. So this is a magnetic dipole that emits such a pattern, and of course this is the dipole radiation pattern. And then we get two sort of orthogonal quadrupole modes that radiate like this. Okay? Then we can take two of these particles and make a dimer. And for the dimer, this mode here is a dark mode. So we have two dipoles out of phase, but still it's able to radiate, not in this direction, but in any other direction it radiates. Here, another dark mode where the oscillations are in this direction, but out of phase, and you get a very interesting radiation pattern here. Then in-phase dipole mode and radiation pattern, another in-phase dipole mode with an interesting radiation pattern. Here, in-phase magnetic modes like this, and this is interesting. Now this you could call that it's a magnetic dark mode. So two magnetic moments out of phase, but still able to emit in certain directions. Okay, so the point here is now that we have been able to decouple the, let's say, the optimization of the structure. We can try designing certain types of structures, let's say with desired radiation patterns and stuff like that, which would then rely on some type of, let's say, superposition of a number of these modes. So we can optimize the structure for a certain purpose. Then once we have done that, we can start thinking separately as how to couple incident light into the structure. And of course, this is not limited only to let's say, nonlinear response. This could be used for any optical response. So at this point, we are, so the remaining challenge is that when we talk about these modes, we could try some other mathematical formulations. There's a possibility that different mathematical formulations emphasize different parts of physics. We don't know yet, but that's a possibility. And then if we take a different formulation, we get a new family of modes. What are the connections between those new modes and the ones we have found so far? A very interesting question. And then finally, how do we couple light to these modes, which can have different multiple characters? And what we want to do, and are already trying to do, is that we want to tailor the polarization distribution of the incident field. Not only radial azimuthal, but use spatial light modulators to control the local state of polarization before focusing, as to produce a desired three-dimensional vectorial field at focus, in order to couple that light strongly or weakly to some funny, complicated nanostructure. A long way to go. It's actually going to be very difficult. I think that the next slide is really promising. Just the end. Okay. So, thanks.